Let's go through some more examples of linear dependence and independence. First, we'll consider example 2 on page 57 of the textbook. So the question there is, are the columns of the matrix A, given here, linearly dependent or independent? This is the same as asking if the homogeneous linear system, the homogeneous equation AX equals 0, has non-trivial solutions. We can row reduce to see the answer. So here I'm constructing the augmented matrix, and I'm looking in the leftmost non-zero column. Top entry of that column is going to be a pivot once I swap rows, row 2 and row 1. There. So now I have something non-zero in that pivot position, and I can use it to kill off the non-zero entries below. So I'm going to get rid of that 5 by replacing row 3 with row 3 minus 5 row 1. First two rows stay the same, and last one becomes 0, negative 2, 5, 0. And now I'm going to ignore that row and that column and just consider the submatrix that I'm left. The leftmost non-zero column, top entry of that column is already non-zero, so I don't need to swap anything. And that 1 I can use to kill off the negative 2 below it. I do that by replacing row 3 with row 3 plus 2 row 2. First two rows stay the same, and the third row becomes 0, 0, 13, 0. Ignore the newly created pivot column and all the columns to the left, that row and all the rows above. This 13 is non-zero, so this is my last pivot. This is now in echelon form, and we have a pivot in every column of the coefficient matrix. That tells us that there are no free variables, and so the homogeneous equation has only the trivial solution. That tells us the columns are linearly independent. So to summarize, the columns of a matrix are linearly independent if and only if every column of the matrix is a pivot column. We can say this in other words. The columns of a matrix are linearly independent if and only if the number of pivot positions in the matrix is exactly equal to the number of columns of the matrix. So something to note, this is something we can compute just using row reduction, and that makes us happy because row reduction is fast. If instead you're asked to check linear dependence or independence for a set of vectors, say v1 up to vp, then all you have to do is stack them together into a matrix with the first column v1 and second column v2 and so on up to vp, and then just use those techniques above. Put the bucket on the floor, as they say. So here's some special cases where you don't actually have to go through the row reduction. So suppose the set consists of a single vector, v. There's two cases to consider. If the vector v is the 0 vector, then the set is linearly dependent. And you can see that by just explicitly writing down a non-trivial linear dependence relation. Right? So this is going to be something like 5 times v equals the 0 vector. And this is non-trivial dependence relation because that 5 is, in particular, not the 0 coefficient. Case 2, the vector under consideration is not the 0 vector. And in this case, the only way to have c times v equals the 0 vector is to have the scalar c equals 0. And so that's the set with just that one non-zero vector in it is linearly independent. In other words, the set v, just the set containing v, is linearly independent if and only if the vector v is non-zero. The next special case to consider is a set with two vectors. Let's call them u and v. In case 1, at least one vector is a scalar multiple of the other vector. So then uv is linearly dependent. And so how can we see that? Well, suppose, without loss of generality, it's the vector u that's a scalar multiple of v. So u is cv for some scalar c. Then minus 1 times u plus c times v is minus cv plus cv, which is 0. And this gives us a non-trivial linear dependence relation because that minus 1 in particular is not 0. So just a remark, if one of the vectors, let's say u, is the 0 vector, then we're in this case because then u is just 0 times v. So if the set uv contains the 0 vector, we're in this situation, we're in this case, and the set is linearly dependent. In geometric terms, we're in this case whenever u and v lie on the same line through the origin. Case 2, neither vector is a scalar multiple of the other. Then the set uv is linearly independent. So now let's take a look at some explicit examples. Linearly dependent sets, well, if I just consider the set with a single 0 vector in it, that's linearly dependent. If I consider a set with 2 vectors in it, one of which is the 0 vector, that's again linearly dependent. If I have 2 vectors and one is a scalar multiple, so if you notice here, the minus 2 minus 4, 2 is just negative 2 times the first vector, 1, 2, minus 1. So it's linearly dependent. What are some linearly independent examples? Well, if I have the single non-zero vector, say 1, 0, 0, that's linearly independent. If I have 2 vectors, neither of which is a scalar multiple of the other, right? And so you can see, maybe it's obvious, but in case you don't see it, the vector 0, 1, 0 is not a multiple of 1, 2, 3, because, for instance, if I wanted to take some scalar and multiply it by 1, 2, 3 and try to get 0, 1, 0, I see by looking at the first entry, the scalar I would need to multiply by is 0. And if I do that, then they don't agree in the second component. Another linearly independent example is this vector 2, 1, 0, and 1, 1/2, 1. So again here, if I wanted to see is one a scalar multiple of the other, well, if I look at the first entries, to go from a 2 to a 1, I would need to scale by 1/2. That makes the first entries agree, it makes the second entries agree, but the third entries don't agree in that case. And so one vector is not a scalar multiple of the other.